Okay, let's move on to the second speaker of this afternoon. That's Giovanni Petri from Northeastern University in US. And he's going to tell us about informational and topological signatures of individuality.
Okay, thank you very much. Close enough. Northeastern University is that one, but I am here in London. So even though I'm not been around that much. Anyway, thank you very much for sticking around this afternoon. I know it's been a long week, at least for me. So let me start by telling you what I'm not going to be talking about, okay? The reason why I'm doing that is because everybody's been talking a lot about math models and so on. So I wanted to, take a change, make a change, but I still wanted to sort of this is a paper that is out there on the archive. You can find it. It's about renormalization, and it's very nice. We are developing like a very nice way of looking at scale invariance in higher order systems in general, hypergraphs and simplified complexes. So please do go and check it out. It's nice. And since we're talking about directed graphs until 2 seconds ago, well, hypergraphs, we also have a configuration model that just came out that is very, very nice and also takes into account directed hypergraphs, but also conserves many other things, as in like correlations, and the whole joint grid, the degree size, directed degree distributions in the bipartite distributions. And it turns out that if you actually do that, in some data sets, you find new things, because that's what we use configuration models for. Now, that said, today is going to be about data. So you can actually relax, sit back, and just like look at the pictures pretty much. So what I'm going to be talking about, well, in the title I had informational and topological signatures. Let's start with the topology. Now, the standard, joke about topology is that it's the branch of math that tells you that a mug has the same topology as a donut. And in typical physicists' answer is like, okay, why do I care? If I have a mug, I want a mug. If I have a donut, I want a donut. The answer to that, which you have heard over the last week, I would say, or at this point, is that if you do have topological non-trivial information, then it's very robust to all sort of transformations, okay? Another thing that is actually very nice to sort of show to network scientists, which is because they don't like, is the founding myth, the origin story of graph theory. Because you probably all know about bridges of Königsberg, but really when you look at this, what's happening is that you're really not interested in any of the properties of the islands, right? You're just like collapsing them down to something that looks like a graph like this. So in a sense, graph theory, network science is really just like low-dimensional topology in this sense, trivial topology. Now, for networks, you have nodes, edges. What do we get extra? Well, we get something, but at least in the simplest case, we get the triangle or the two simplex if you're in simplified complexes, which is not just sum of the edges, and typically you write in some way of this type, okay? Now, for the people that are familiar with multivariate information theory, this looks a lot like the kind of the multivariate information probability distributions that you look at in multivariate information theory. And that is true, right? Because intrinsically, both of them are higher order in the sense that we intend. So the fact that you're describing interactions between more than two bodies in this sense, okay? The thing that is nice about topology, or at least topological descriptions, is that if you have something like this, you end up having holes. And in a sense, and with abuse of notation, let me say that are intrinsically non-local, okay? Because to have this kind of holes and to see them, you need the coordination of a bunch of edges around, okay? Now, what is the problem in using this for data is that, when you do presentation, when you make presentations of this type, you typically have very clean, pretty pictures like this, okay? Especially when you like do graph theory, not even network science that has like more noise, but this is nice. And it's very nice, and even if it changes in time, it opens up, it closes down, it's a sphere, it's very clean, it's very pretty. Our brain is very good, surprisingly, at picking up topology, shapes. We don't really know why we're so good at that, but we are. The problem is that, here you probably don't need anything from homology, percent homology, TDA in general to figure out these changes. You could measure the distribution of path lengths, for example, when it's open and when it's closed, you figure it out. But now try doing the same thing in something that looks like this, okay? Now, the image you're seeing comes from a conspiracy website. I am not kidding. They think that's the shape of the universe, I guess the Wicker universe or something like that. The pink noise on top, it's my feeble attempt at, well, making noise there. But then the question here is this a sphere, a large sphere? Are the holes important? Are these like little features on here important, and so on? And the question becomes, how do I actually, quantify that? That's where going back to, topology, or at least topological data analysis helps us, because you would like some sort of discretization of data of this type, and you've heard yesterday from Omer, and I have some other people too, that one of the classic way in which we can do this is, for example, by basically fattening balls, right? So you put a legal ball around every point. Whenever two balls touch, you put an edge. When three balls touch, you put a triangle, and so on, and then you go on. Then the question becomes, okay, what is the scale? How big should your balls be? Pun intended. And precision homology says, well, let's turn the problem upside down. Let's look at all the different radii that I can look at, right? And so by construction, at least in this construction here, you have a chain of inclusions, so it's very easy. You can put like simple complexes one after the other. And then you can start counting topological features. Topological feature is a fancy word to say, connected components in low dimension. How many the connected components do we have here? How many one-dimensional holes? How many two-dimensional holes, and so on? Okay. Now this looks a little bit like magic the first time you do it, but the beautiful thing is that you can actually then compare quantitatively shapes, right? You can look at something like this, and you can say, well, I would like to have a measurement that tells me that these two guys down here are more similar to each other than they are to this other guy here. And, and these guys sort of more different to these two guys than they are to each other, okay? So this is what, the classical persistent homology approaches allow you to do, and you have like a bunch of ways in which you can actually measure these distances between persistence diagrams, persistent landscapes, and so on. So the typical pipeline is that, well, barcodes are not really in use anymore because we don't like them. So we like persistent diagrams, and you heard it yesterday. And the general pipeline is something of this type. You start from some data. You have a way of producing a filtration, which is that sequence of simple complexes. In the classical case, it's an inclusion chain. If you have zigzag homology, you can have fancier thing, doesn't matter. You end up with something that looks like a persistence diagram. You measure distances, you can have kernel similarities that depend on parameters and so on, and then you do everything down the line, okay? Now, I've told you this, now you can forget it, because we're not gonna use persistent diagrams anymore throughout the rest of the talks. And actually then the question becomes, why am I talking about this? And what does this have anything to do with brains, okay? Now that's a zombie, but it's also a little bit high, and there is a reason, because probably the functional topology of a zombie is altered. So let me tell you the story. So this story starts a few years ago when Paul Expert was here yesterday, and then when he knew that I was going to talk about this, just ran away, gave me data from the Imperial Psychedelics Lab on people that were injected with psilocybin. Now for the naive among you, psilocybin is the active principle of magic mushrooms. Okay, so these people were high as kites in the scanner. They were also recorded another time when they were not high and they were on placebo. They weren't told, of course. And the interesting thing is that in the original papers, basically this was the only real difference that they found between the two conditions. Okay, by looking at the activations of the the bold signal, which is basically how much oxygen is consumed by your brain at a certain time at a certain point in space and point in time. Problem is that the self-reports were massive. Showed massive differences. So these people were reporting ego dissolution, great changes. This didn't really make sense, right? And they were looking at the networks, and they weren't really finding much difference, in terms of the structural connectivity of what is called functional networks. It really, literally is take the time series of your Boole signal from every region, make a correlation matrix, call it a weighted network. That's functional connectivity in neuroscience, okay? It's loved and hated, but it works. So what did we do? Well, we actually pretty much did the same thing. We considered those correlation matrices as a metric space, so we could do the persistent homology approach, that I described earlier, poles in this correlation space, and we end up with something that looks like this, okay? Now, these are group persistent diagrams. in a sense that we just put together all the dots that we had for the two groups, 15 subjects, well, the same 15 subjects. Once they were highs, once they had placebo, and another time they had psilocybin. It's flipped just so that it looked prettier. And we saw this and we're like, well, there is a clear difference between people that are under psilocybin and people that are under placebo. Right? This is H1, so one-dimensional cycles, okay? At the time, computers and code was pretty bad, so we couldn't go higher. Then what we could, we didn't find much signal anyway. Now, then you go back to your neuroscientist friends, you show this triumphantly, and they tell you, okay, so what? I mean, we know they're high. We know we gave them psilocybin, so the point is, what is different? And this is, if you want, a general problem when you have this kind of topological descriptions. And the problem is the localization of topological information. Okay, so there is a difference. Where is it? Okay. And so we did something that every self-respecting mathematician should never do. We ignored equivalence classes. And so we defined something that's called a scaffold. How do we do that? Okay, let me remind you what happens when you have a filtration. So you have this sequence of simple complexes. At some point, there is in H1, so one-dimensional holes, but it generalizes. We never did, but it does if you want to. You look at when some feature appears, it lives for some time. Okay, that's the persistence. We could redo this with the persistent, the death over birth of Omer yesterday. It doesn't matter. I mean, we did it with the persistence in this case. And the problem is that what you would like to do is to go back to something where we can actually localize the information. So what we did is that we chose a representative for the homological class. So one of the boundaries. What is the problem? The problem is that, you could, if you have other triangles around, you cannot take other cycles, right? So you don't really have a perfect choice. So what we did here is that we just did it, and we checked later that it didn't make too much nonsense to do it. But, pay when you with the construction, so you just do this, and you basically select a cycle, and you put it back in a new graph where you have no edges. You put the edges weighted by the persistence of the cycle. We were trying. At the time, we didn't really have much control. So we were trying to take the shortest at birth, and that's not always unique either. So sometimes we're tricking a bit, but then we're checking afterwards that it wasn't too bad. So they were not changing very much. I can tell you, we're trying to do this now with harmonic cycles. It makes some sense, right? At least the point is that it's not always unique. You're not always sure you get it because anyway. It's roughly, I mean, in theory, it's one of those cases where in theory it's bad, but in practice it actually works, right? You can do it, yeah, exactly. So you do that, and you end up with a new weighted graph. Okay. The magic of this is that this new weighted graph is extremely sparse, and there is no guarantee that it should be, but it is. And just to show you, this is an example for one subject. There is a adjacency matrix down here which you can't see because it's very sparse. Just to show you that it's not just a thresholding of the system. If you threshold the original functional connectivity matrix, the correlation matrix, at the same density as this guy, you end up with something that looks like this. I know it doesn't look like it should, but it does. If you instead do another thing, which is you pick the edge in here that has the minimum value in the original correlation matrix, and you threshold that level, you end up with something that looks like this, okay? And even just by eye, you see that this guy is very different from this guy, okay? So we're not just thresholding this matrix in some sort of strong version, but by construction, right? Because we're doing a multi-scale process to extract this scaffold, Even if you have some noise here, the construction is multi-scale. So we did this for the two groups, and you end up with something that looks like this. On the left, placebo. On the right, psilocybin, okay? Now, the colors were very pretty. And so that got a lot of attention online. But even just by eye, you can pretty much see that there is a lot more difference between these two guys here than over here. Okay. I think that I didn't do it on purpose when I made the plot, but I think it played a role. Something that people, I mean, if you look at the people that cite this paper, they say, oh, there is a lot more connectivity in the psilocybin case. This is actually not true, right? Because this was built by looking at the cycles across scales. So really, the way you would say it is that you have a distributed reorganization of the hierarchy of functional circuits. Okay, that's how the neuroscientists would like it to be said. Okay. If you remember, I spoke about fingerprinting to begin with. Okay, this was about fingerprinting, so saying who's who. So more recently, what I'd like to tell you about now is that we took a bunch of subjects, 100 subjects, recorded twice, now and in 2 weeks. We have a long time series, and so you can take windows. And for every window, you can build one of these graphs. You can build the homology. You can compute the homology and then compute the scaffold. Okay? And for example, you can do fancy things like go and look how different the functional connectivity matrices are in time, how different the scaffolds are in time. You already see some pattern there, right? The thing that we're interested in here is fingerprinting. So can I tell how far I am from each of you? And then you give me some other matrices and I can say, that's my matrix, right? Can I actually pick up myself? Now, we did this with 100 subjects. And I'm going to show you a zoom. And if you do the functional connectivity, you end up with something that looks like this, right? And if you do it with the scaffold, you end up with something that looks like this. And red means very close or very similar, depending on. So if you do it for all the subjects, you end up with something that is brutal like this. So the identification rate of subjects was using the scaffolds rather than using the functional connectivity was amazing. You can put numbers on top of this. You can look at the effect sizes of the distance between you and yourself in the future, and you and the others, functional connectivity, and the same thing for scaffolds, and you see the effects are huge. Now the effect sizes are so big that I actually didn't believe it. So we redid it 3 or 4 or 5 times. I don't remember anymore because this was the Simone that was doing the code, and I was like, this is too good to be true. Come on, you're comparing subjects within the same session, not within this session and the other session. No, it works. It turns out that it's actually true. And to be fair, it's not that functional connectivity is bad, right? It's just that the scaffold is so much better. Okay. This, of course, generalizes for different window sizes. You remember, because I said there are multiple things you can say. It doesn't really matter. The effect is always there. So it seems that these scaffolds are extracting something that is extremely powerful in your case and subject. And then if you are a little bit in neuroscience, you know that people talk about functional networks, but they really mean functional subnetworks. So there are some parts of your brain, a frontoparietal network, default mode network, and so on, that have some assigned function, or at least more or less identified function. So you can actually repeat this game by subnetwork. And it turns out that still, you have pretty good effect sizes. You have different effect sizes, so different capacity of the different subnetworks to identify you. For example, the frontoparietal and the visual network are very powerful in terms of compared to the other networks. So something that I didn't show you here, and I forgot, is that, because I thought it was there, but it's not, is that if you actually redo this at the subnetwork for the functional connectivity is better than the scaffold. So it seems that this is something that is defined, at least from the way we computed, at the level of large-scale hierarchy, architecture of the brain connectivity. Okay. So beautiful. The fact that the frontoparietal is very different between people sort of makes sense because it's our attention mechanism and so on. The visual is surprising, right? Because you would imagine that we more or less all see the world and process information the same way. Apparently not true. Okay, apparently it's extremely idiosyncratic the way you process information. Beautiful, it works. I have no idea why it works. Okay, actually, I have quasi no idea of how it works. And here it's where the information theory comes in. So a lot of the conversation right now in neuroscience, at least in network neuroscience, it's about synergy and redundancy, which is the other face of the medal with respect to topological data analysis in this world, right? So the idea of redundancy and synergy is that you have 2 sources and there is information that is shared by them, and that's redundant. It's copied information. There is information you can only access by looking one and it's not present in the other, unique information, and then there is redundant information, which is the one, synergistic information, the one they can only access by looking at them both together. Typical example is stereoscopic vision is synergistic, color is redundant because each eye can see it, and so on. Okay, unique is just the part of the field of view that the other eye doesn't see. Okay, there are multiple camps. There is the Sporns, Varley, Tononi camp, which is like a large information theory, and this is done actually by computing information, redundant information and redundant and synergistic information over triangles, and then projecting down to edges. And they have some results showing that the synergistic part seems to be the one that is more different among people in terms of community structure of this induced graph. We didn't do that because it's very expensive. So we actually adopted the other camp in information theory, which is Andrea Luppi, some of the early work by Fernando, Rosas, Pedro this morning, and so on, which is basically time-delayed mutual information. So you look at how an edge can predict its own future. Okay, so you end up with mutual information that predicts your own at the edge level. So naturally, you can have a redundant and a synergistic graph induced by that. This is their work, right? And then you can show that the redundant part tends to be correlated with correlation. Again, not surprising. Correlation is going to tell you about the same information, and so on. So we played the same game. So we ended up with uglier plots because we're not going to put this in the papers anyway, but they correlate with the others. We define the same level in terms of, you find that the scaffold, the correlation of the edges in the scaffold tends to be higher than the one at random, if you pick at random, but that's not surprising because when you do the filtration on a correlation matrix, you start from small distances, which is high correlations, right? So it's normal, they emerge first. The cute part is that if you look at the redundancy and the synergy of the edges in the scaffold, they are different. This is significantly different from picking edges at random, but not much. Okay, so these are not, the edges in the scaffold, they're not particularly synergistic or particularly redundant. They're just a little bit, they're mediocre. They're not that different. Okay. Turns out that we're looking at this the wrong way. So the right way of looking at this was actually focusing on the cycles themselves. Okay, so now let's go back to how you build the scaffold, right? You have a cycle, persistent cycle, you take one representative, and then you sort of weight it, right? Then if you go back, you can actually look at the cycle that you had. You can look at all the edges that are going to be in there. They're closing it. These we're calling boundary. These we're calling internal links. And then you can ask, are they special in any way? And then turns out, yes. So now give me a second to sort of help you parse this plot. So these are the internal edges, okay? And they are the highest, right? You can see it in terms of the most synergistic. These are the edges on the boundary, and they're less synergistic. These are other edges that have the same distribution of correlations. On average, they have the same amount of correlation, but are sampled randomly and they're not on a boundary. So you see there is no real difference here. And the same thing if you take these other edges that are not in the interior of a cycle, but have the same range of correlations. So basically, we're just correcting for the effect of potential effect of correlations, okay? So what we're really telling you here is that the scaffold is very, very good at building, at discriminating. And what it's seeing is islands of high synergy, localized islands of high synergy. So so the boundary in a sense is that where this island of high synergy stops, that's your cycle. That's the one that you get, okay? And so it's putting it together. So summing up, we have this kind of topological information discriminates super well across individuals. We have this mesoscale again in the sense that these cycles are not the whole network, they're not super local, they can be of any size, and they're very, very powerful. We found a relation to, let's say, local information theory measures. Again, I've given you a link, but I don't have any idea about the dynamical origin. So we haven't reproduced this, for example, with computational whole brain models yet, okay? We know that there are some links, but we don't know. Finally, even though I showed you that it's possible to do this on multiple windows, the time scales are still long, right? We can go down to about 100 time TRs, which is about a couple of minutes, roughly. So it's still not instantaneous information, okay? So we're asking, well, can we actually do better? Or what happens at smaller time scales? And so to do that, we sort of picked up on a paper that published a couple of years ago. A year ago and a half. Anyway, recent, but not so recent. And in which we cheated a little bit. So we basically used we generalized a proposal by Rick Betzer and others to construct time series for edges, triangles, and so on. So you have times 2 time series, you basically normalize them properly and you multiply them together. So you look at the co-fluctuation time series. And then the same thing you do for 3 and so on and on and on. Okay. There are all sorts of problems with doing that because, if you have a Gaussian process, this is trivial, but if you go to higher order, this is not the case. In particular, if you have you have to make a decision about the sign, right? When you have 3 edges, you could have 2 fluctuations that are plus and 1 conflutation that is minus, so you will get a minus. But if you have 2 minus and 1 plus, you will get plus, right? So you have to make decisions. So what we did here is that we chose absolute uniformity, or I think we call it Nazi coherence at some point. So basically, everything up or everything down is plus. If not all the fluctuations that have the same sign, then it's a minus, okay? Why this is beautiful? Well, because at this point you have a weight for every node, every edge, every triangle, everything for every time. So you can actually build for every single instant in time a weighted correlation, a weighted simplicial complex, right? So now we can do persistent homology again with one caveat that the weights have no reason to be in the right order, okay? So what we do is that we start with the nodes and we start from the positive weights and we start putting them in. And whenever, for example, a triangle comes in before on one of its edges, we say that it's a violating triangle, we set it aside, and we continue. So we end up with a list of violations, triangles in this case, and a cleansed filtration. This is a valid filtration. From the filtration, we compute the persistence diagram, H1, H whatever, in this case, H1. And for what I've told you, right, we go from positive weights to negative weights. You have 3 sectors in here, right? Coherent, coherent, so positive weight to positive weights, positive to negative, and negative to negative. And so you can actually basically normalize how much persistence you have in here in like a little triangle of this type. Okay. So, well, we didn't know whether it worked, but the construction summarizes that you end up with a simplicial complex. With a simplicial complex, you end up with a list of violating triangles and some sort of topological information on that side, right? If you count the persistence, you can do the homological scaffold hypercomplexity. For hypercoherence and hypercomplexity, we just intend the number of triangles that are violating and the amount of persistence that you have in there. Turns out that if you do this on, for example, simple dynamical systems in which you can control the dynamical regime, you end up pretty good at discriminating the dynamic regime, chaos or intermittency and so on. Okay, so it works. And you also induce scaffolds that have different weight distributions. It works, and we're very, very happy. And originally what we did then was, okay, so let's compute the hypercomplexity for a bunch of dynamic regimes in a model. Let's do it for brain data, financial data, epidemic data. We came up with a little null model in which we're randomizing a time series, and that's the gray one. And you can see that there are some differences, okay? Now, let me just show you quickly. I got that, yeah. One example, and because we're never gonna publish this, but this is because Bispignani kills me for it, but let me show you this privately. The beautiful thing now is that, if you go here, you have basically for every point in time, you have 3 numbers, right? So the coordinates here, and you have the complexity. So you have this low dimensional vector. So for example, if you do this on time series from epidemics, right? For example, in the US, you end up with and every time series is in a different county of the US, right? You end up with 1 vector per time point per disease. You embed it, and then you see even just by eye that if you know which disease is which, you can actually see that it distributes differently in this space. Beautiful thing is that you can actually train a classifier for the disease on this 5-dimensional data set, and you end up having pretty good results in terms of classification. And this is the part that is in the paper. The part that is not in the paper is that you can play, right? Because this classifier only sees that little vector, 5-dimensional vector, right? Extracted from topological factors, from topological features, and take COVID data from Italy that this classifier has never seen, and play the same game and ask the classifier, what do you think COVID looked like at a certain point in time, right? And so this is Italy. These are different diseases that the classifier has seen. And then it tells you that, for example, during the first lockdown, it looked like hepatitis, which makes sense because you basically have to sit on somebody to get it. Then during the summer of freedom, when the first lockdown finished, it looked a lot like measles from the point of view of the classifier. Then the second lockdown was more mixed. It looked like polio, which has a different R0 and different spreading pattern, and so on and on and on. Christmas of love, when you had to see your friends and so on. And then when the vaccination begins, this is all crazy, right? The reason why I'm showing you this is that it's a fun game, right? But it's actually telling you that it seems to be picking up something interesting. mixing together dynamics and space. I don't know what, but it does. But I want to show you. Now back to brains before I lose my job. So what did we do in this case for the time resolved analysis? So in this case, we have a different data set. So apologies for the change in color palette. And we have a bunch of tasks. So we don't only have resting state like we did before. We basically reproduce the same game. We do everything like before. We end up with something that looks like this. And the result is there is nothing. The tasks all look similar from these global topological descriptors. And so we tried to go down, and we basically we created representations of our data set at nodal level, basically ball signal, edge level, edge connectivity, triangle level, and topological levels by projecting the number of triangles that I have, and so on and on and on. And the beautiful thing is, since you have one per time, you can actually look at the correlation over time. So you end up with little matrices per subject in which you can basically say, well, if each of these blocks is a task and they're perfectly different, I'm going to have like a diagonal structure like this, And then I can do this for the various quantities that I showed you. And the thing that you find, and you end up finding, is that basically as you proceed from low dimensional descriptors, node level, edge level, triangle, and scaffold, the correlation within task gets better. So what this is telling you is that these higher order topological features discriminate tasks better than the other, but using local information, because here you have used the scaffold, the triangle. So you're using the cycles, but you're projecting now. Using the triangle, you're projecting it down. So you keep that information. It's not just the numbers. Then, of course, you can go back and do the same game with fingerprinting, right? So you end up with something that looks like identifiability matrix. Again, my apologies, different sets of people doing this. Some people like effect size, other people like something they call IDIF, but the idea is the same. And the result is pretty surprising. Here you can do, so when you do fingerprinting using these time resolved features, you have very, very bad results at the global level. If you then go locally and you look mesoscopically, you go at the functional network level, you have differences in how well you do differentiation using violating triangles, edge, and bold. So triangles, edges, and bold. And there is one part that is missing. There are no scaffolds here. Scaffolds are really just bad here. Okay, so at the super fast scale, the scaffolds we build are not really good, but overall, the triangle structure is always more idiosyncratic, better fingerprinting than the other descriptions. You can actually look at the variability. I mean, this is interesting only if you know the neuroscience, but you can do this you can actually count how many triangles are in one node, in one subnetwork, and two nodes in different subnetworks, and so on. You can look at this, but it's just, it's pretty to show, but it's not really important. Summing up, so I showed you that we have this kind of global higher order indicators that are not really able to distinguish between rest and tasks, okay? The local markers, scaffold, they work very well. The local higher order information that can be used to discriminate tasks, but only at the triangle level. So now we have this conundrum, right? So if I go global in the sense of scaffolds at the whole brain for long time scales, I actually can discriminate very well. But then at local time scales are really bad, and instead the thing that is very good are triangles, even though the constructions are very similar, okay? Because they both come from these kind of topological things. So we don't really know what's going on. We are looking, Marilyn Gatica, which is one of the postdocs in Northeastern now, she's trying to see whether with computational models we can actually simulate this, can reproduce this. That at short time scales, it's the local triangular features that are really important, and then basically it reverberates somehow to create scaffolds at longer time scales. Okay, but we don't really know, so we're there. With that, thank you. These are the people that are involved. Let's say the first part of the people are involved in the first project. Second part of the people are involved in the second project. There is some sort of higher order effect there. Couple of shameless plugs in case you're interested, and thank you very much. Yes.
To what extent can you use all these methods for clustering? I mean, you said topological information discriminates well between individuals, or putting colloquially, every idiot is different. Yeah, but somehow you also want to identify groups of people.
Okay, we haven't tried. Yeah,
You want to discriminate between different
groups. So you.
People are healthy and afflicted people and whatever.
Okay, wait, I didn't show you. The original title was Individuality and Age. There is a different construction, but it's related. And I'm just going to show you this quickly. We can actually do this in different measures for age groups. Whoa, not wrong. No, this is, sorry. So this is, anyway, I'm not going to try. It works for age too. The main effect seems to be individuality. So you. We do know that if you don't, so we didn't really test it systematically, checking for all the factors. So I can pick up states, placebo, psilocybin. I can pick up individuals. Can I separate the two? I don't know yet, but actually this is a very good point, because so something that I didn't say, which is not, we have not tried at the temporally resolved way, so the second part, but the first part is you can actually also check how good the functional connectivity is within the same session. So not from now to 2 weeks, but from now to 20 minutes. And the same thing with the scaffold. Scaffold is still better, but functional connectivity gets better. So this is telling us that functional connectivity has more information about, let's say, state right now, while scaffold has more information about what they would call, neuroscientists would call traits. So something we would like to do, we haven't done, is take data from twins, take data from families, and see whether we can actually see this kind of thing.
Connectivity is similar as the people in similar moods, or as they doing similar tasks.
Yeah, I mean, we know that there is that. We haven't done it with the function, with the scaffold too, and so it's hard to compare them to see which one is better. But definitely there is that. I tend to think that, scaffolds tend to be sort of more stable. And for example, they should be a good candidate, for example, for tracking of neurodegeneration, right? Because you could have MCI, but one day you're good, one day you're bad, but you still go in the direction. It's being computed, but I don't have the results yet.
I think there was some other question.
Thank you, Giovanni. I didn't get something when you compare with the redundancy and synergy.
Yeah.
Say that you did at the local level the randomization of internal links, right?
No, there is no. You mean? Wait a second. You mean this one? This one? No. Sorry. Yeah, I skipped on a little bit. So you can take a cycle, right? And then you have the edges inside. Now, the edges, all the edges that are inside cycles, they have a certain correlation distribution of correlation values. And I don't know whether the correlation has an effect on their synergy and redundancy. I know that it does, but I want to correct for that. So what I do is that I sample other edges that are not inside any cycle, and I sample from the same range of correlations, so that I know that I'm correcting for the effect. And that's what it's happening. The random is that, yes, again, that's why I said this is not going to the paper as it is, because then people ask that question. Yeah, but that's what we're doing. Yeah.
In the morning titles that it's challenging to tackle the synergy and the redundancy and checking the old information and the RSI and stuff.
Yeah.
Right here, it's easy for you to tackle that.
It's that I have a big computer and small atlases. Not really so small, but the atlas we're using here, it's about 300, 400 regions and a very big computer. So the Sheffer, yeah, exactly. No, it is. I agree. It's hard. It's just that we were patient, and that the reason why this thing has been in how you say, in preparation for a long time is because we kept finding new things. So, for example, something I didn't show you is that we also have randomized models for the time series that conserve the correlation matrix as asymptotically, so for long time series. And for example, if you do that, but then you still do the windows, you see that the windows are different. They're not as good at fingerprinting than the actual data. So there is something there and so on. Yeah, no, I agree. It's long. It's just that, you know, if you are sufficiently motivated, you just let it go. Yeah. There is another point. I wasn't here for Pedro. I'm sorry, because I heard him many times. The other problem is the length of the time series. Of course, how many data points you have. These are very long time series for the standards of fMRI. That's why we chose them. Okay. Yep. Okay.
Which redundancy and synergy methods which you actually use?
Which one? The Andrea Lupi, the time delayed mutual information. So the edge level. So edge versus the edge predicting its own future of the two nodes and that. That's because it was easier than the full Varley sports. That's really heavy to do. That's what we do. And it's less data hungry. But of course, we should do the other two. It's just that we're patient, but not so patient, right? So I want to get something out.
Let's thank first.
Thank you. Thank you.